So welcome everybody to the PEI Masterclass series. PEI stands for Polar Educators International, and our mission statement is a vibrant network promoting polar education and research to a global community. The PEI Masterclass series class tonight is looking back to the future using paleoclimate data to understand Antarctica's ice sheets. This is the third masterclass in the 2014-15 series. Our next class will be offered in the fall of 2015, and details about that will be announced soon. Hopefully all of you have visited polareducator.org. Notice that for the web address, there is not an S on educator. And this is the place that you'll go to join the discussion forum, become a member of Polar Educators, which I think most of you have done now. And this is where you can learn more about Polar Educators International. Pretty excited to look at the map tonight. We've grown from 46 countries during the last webinar to 86 countries of members. So Polar Educators is growing and making quite an international impression. So we're excited about where this is going. Our vision statement for PEI, Polar Educators International, is a vital international network of educators and researchers aiming to provide a deeper understanding of current polar science. PEI represents trusted leaders working to inspire appreciation and knowledge of the polar regions, their connectedness to all Earth systems, and importance to all humans across latitudes and cultures. One of the ways that PEI is working to meet the goals of our vision statement is to sponsor master classes like this one, focused on the needs of a dual audience, educators and researchers. Before we start our webinar tonight, I just want to remind you to be sure to join the discussion forum, which runs from March 4th to the 20th. And I'm just going to give a quick tutorial on how to sign into the discussion group. The archived webinar announcements and discussion threads for this class are held in the members area of the PEI website. And to join the masterclass group, you go to Polar Educators or polareducator.org members, and you'll log in. There's a picture down here at the bottom, but the really important thing is to click on Remember Me before you log in. You'll put your username and password, click Remember Me, and then log in. And this will say, you'll be really happy to do this because it'll prevent you from having to re-log in every time. And there's a software glitch that we're working on and working around at the moment. So be sure you do that. When you're logged in, you'll be on your home screen. The top menu bar shows friends, groups, and photos for all of the member area. You'll click groups to find the masterclass discussion group. Then you should see groups you are a part of. Click all groups to see which ones you can join, and select masterclass discussion looking back to the future group. Select join group on the right, and once an administrator approves it, you will be in the discussion group. It's not instantaneous, but we'll do our best to be responsive. Okay, on this slide, we've put up a direction sheet. And if you go to Activities, Masterclass, Looking Back to the Future, and then the Syllabus and Registration page, you'll be able to go about halfway down the page and find a link to the details of signing into the discussion group that we just went through. So a couple of important reminders. Be sure to sign up for the discussion group that's going to start tomorrow at polareducator.org/members. And then if you have any technical problems, you might want to write down this email address. It's polareducators2@gmail.com. And notice that there is an S on educator in the Gmail address. So tonight, if you have questions during the presentations for either Dr. Atkins or for Betty, what you're going to do is In your control panel, there's a blue line, at least it's blue on my screen, but it says questions. You'll type questions into the box. We'll pose them to our presenters at the end of the presentation. If we don't get to all of your questions tonight, they'll be answered in the discussion group between March 4th and 20th. So it's my great pleasure tonight to introduce our speakers. I had the opportunity to work with Dr. Cliff Atkins during the Andrill project in Antarctica in 2007, and Betty and I have worked together on many polar projects since we met in 1992. Betty and Cliff have worked together since 1998 and exemplify the model for how educators and researchers can work together and collaborate on a wide variety of projects. Dr. Cliff Atkins is a senior lecturer in the School of Geography, Environment, and Earth Sciences at Victoria University of Wellington in New Zealand. He's a geologist whose main interest is interpreting sedimentary processes from strata deposited in marine and glacial environments. His glacial work has largely been in Antarctica on drill core from 17 to 34 million years ago. Betty Trummel is a veteran educator with 35 years of elementary classroom teaching experiences, most recently in Crystal Lake, Illinois. She has taught science methods for elementary teachers at Northern Illinois University for 10 years. Betty has spent 3 research seasons in Antarctica as part of educational outreach programs for the Cape Roberts, Andrill, and Wizard projects. These projects provided the opportunity to spend months working alongside outstanding science researchers. She strives to bring the voices of those scientists and their experiences back to not only her classroom, but to many others through broader outreach on local, national, and international levels. I'm honored to welcome Cliff and Betty to the Masterclass series, and will now turn my screen over to Dr. Atkins. This will take just a second. Okay, so Cliff, you should see the button to take over the screen, and you'll need to unmute your microphone. There you go.
Okay, that looks good to me. Can you hear me all right?
Yeah, you sound great.
Excellent. Okay, thanks for the introduction there, Louise, and welcome to everybody from around the world, wherever you are. It's a nice summer afternoon here in Wellington, but I appreciate that it's fairly late at night and probably in the depths of winter for some of you. So I'm pleased you could all log on today for this masterclass, looking back to the future using paleoclimate data to understand Antarctica's ice sheets. I'd like to start by acknowledging a few other people who have contributed to this. I've used a lot of diagrams and a lot of slides in my presentation today from various members of the science team from the Andrill project, and in particular Professor Tim Naish and Associate Professor Mike Hanna from Victoria University. Okay, so I'm just trying to get my slide to advance here. Okay, here we go. So as Louise just mentioned, Betty and I have been working together for many years, 17 in fact we worked out recently. It started on the Cape Roberts project in 1998 when Betty was one of the teachers experiencing Antarctica and I was working on my PhD. And we got talking about education issues and having a passion for education, and we kept in touch and worked together, and that continued on through the Andrill program. And I've given talks at Betty's elementary school, Husman Elementary, and in turn Betty has given presentations to my university class here at Victoria University, and we have jointly run teacher workshops in New Zealand. So it's been a learning experience for both of us, and it's really impressed upon me the importance of having good communication to get the messages from science out to a wider audience. And I think everyone listening in today can remember one or two teachers in their education history that have really made a difference because they have been enthusiastic and passionate about what they're talking about. So that's something that I find a huge motivator and something we can talk about today. I want to start with this diagram and set the scene, and this is something the previous webinars have also mentioned. Here we have a graph from the IPCC. We've got carbon dioxide in parts per million going back over the last 1,000 years or so, and projected rise into the future. I don't want to talk in detail about this, but I want to make a few key points. And one is greenhouse gases are rising. Global temperature is rising. And the human influence on the climate system is now clear. So I think, you know, we need to accept that now, despite what you might read in some media from the science community. This is absolutely clear. The evidence is overwhelming. If we look at the projected sea level rise scenarios, there's a range there, but we're looking in the order of perhaps a metre of sea level rise by the year 2100. If we want to go back more than 1,000 years, we have to go back beyond this graph, and we have to look at the carbon dioxide record from ice cores. And this can take us back perhaps 800,000 years into the past. So you can see age along the bottom here, carbon dioxide in parts per million up the side. The key point here is that the 2015 concentration of carbon dioxide in the atmosphere is now about at least 25% higher than at any point in the last 800,000 years, at any point through the last 8 or so glacial interglacial cycles. If we want to look further back in the record, then we actually have to look at the geological record. So carbon dioxide record from the geological record. So this is one of the more complex diagrams I'm going to show today. You don't need to know the detail of what all of these little blue triangles are, but they are paleoclimate records of carbon dioxide stretching back for over 3 million years. And the key point I want to show here is that the 2015 concentration of CO2 has not been at this level for about 3 million years. So we have to go back into the Pliocene if we want to see what the world looks like with a CO2 concentration of over 400 parts per million. So my point here is the paleoclimate record is very important. It is our window into how the world might look in the future. That's important, of course, because we know that carbon dioxide is linked to climate warming, and we know that climate warming is linked to sea level rise. So this is a diagram from the latest IPCC, courtesy of Tim Naish from the Antarctic Research Centre. The points here I want to make are that glaciers are melting and sea level is rising. The current rate is about 3.3 millimetres per year, but that is expected to increase quite dramatically in the coming decades. The rate of increase will depend largely upon the response of the big players in the climate system, and I'm talking about the ice sheets in the Arctic and in Antarctica. So perhaps we're looking at a metre, but perhaps a lot more than a metre of sea level rise moving into the future. Now, I don't need to point out to everyone listening today why that is a problem. So let's move on to Antarctica, and I can try and impress you with all sorts of facts and figures about Antarctica. You know, not only is it the highest, driest, coldest and windiest continent on Earth, it has the largest ice sheet in the world. It holds about 90% of the world's ice, and if all of that was to melt, sea level around the world would go up by something like 65 metres. And I'm not suggesting that is about to happen, but I'm trying to make the point that there is a tremendous, a staggering amount of ice in Antarctica. Antarctica and its ice sheets are major players in the global ocean circulation and in the climate system. And importantly, the West Antarctic ice sheet is important because that is the one that sits mostly below sea level, and so it is at risk of ocean warming. So this leads me to ask 3 big questions, and I'm going to refer to these as I go through the talk. When did these big ice sheets first appear? How have they behaved through cycles of global climate change? And importantly, how will they respond to a warming world in the coming decades and centuries? Right, before we go into that, I just want to have a look at one of the communication tips I've come up with. And I'll start out by saying that These communication tips I'm going to talk about are not the result of any detailed pedagogical analysis on my part. It's simply things that I have learned through my 15 years of teaching about Antarctica. Some of them will sound very familiar to you, and in fact I note that a lot of these points were also listed down in the Communicating the Science of Climate Change and Making Effective Science Presentations documents that we read before this webinar. So first of all, know your audience. What do they know and what don't they know? This is, for me, one of the most important things that I have done to make myself an effective lecturer. I try and put myself in the student's shoes. What did I know about this topic before I had studied it? What were the things that I didn't understand and that I stumbled on? And if you can remember those things, you have a perception about your students. I think it shows some respect for your audience that you've tried to think about that, and it means that your presentation will be at an appropriate level. So that is my next point here. Make sure the things you are presenting are at an appropriate level. Don't go and present a diagram like this one to your elementary school students or even first year university students. There is way too much information here. There's lots of squiggly lines, lots of numbers that you can't see properly. It might make sense to one of the Andril scientists, but to everyone else there's a whole lot of noise. And that's very distracting and it will turn people off pretty quick. The other point I'd like to make is that people need some context. Why should they be interested about this topic? And you've only got a couple of minutes to grab people's attention. So hopefully the slides I've already shown have given you some context about why paleoclimate is important. It is relevant to us and it's relevant to how the world will look in the coming decades and centuries. If I was talking to a group of kids, which I do on occasion, I would totally change my approach and I would offer slides that look like this. Keep it simple. Where is Antarctica? I mean, really, how often have you seen Antarctica represented on a map properly? If I'm talking about the ice, I want to say it's big, and 14 million square kilometres might not mean much to a child, but being able to say it's 57 times bigger than New Zealand or twice the size of Australia might actually mean something. Now, what does a cubic kilometre of water look like? Well, I've got a little Google Earth diagram here showing what a cubic kilometre of water looks like superimposed on Wellington. So it's a visual trigger to try and get across the numbers and the importance of what you're talking about. The second communication tip I want to introduce is building rapport. And I've always understood that this is an important one, but reading through Gary Lewis's document on giving effective science presentations, I see that up to 40% of the impact of your talk comes down to the rapport that you build with your audience. So a way that I do this with students is showing that I'm a human just like they are. It disarms people. So throw in a little bit of humour, be interesting, let your enthusiasm show. Without getting too carried away with it, sometimes I show a picture of myself at the bottom of the world standing on my head, or I have a laugh at my own name, Danger Cliff. This is a sign from a ski field that one of my students brought in. For my second year sedimentology students, we have a little in-joke here, sedimentary, my dear Watson. They all think that's pretty funny. Or I show them this picture of Uncle Sam, but with Charles Darwin's face superimposed upon it. So something just to lighten the mood a wee bit. The one that usually works really well is showing a picture of an Antarctic field camp toilet, and it's a strange thing to show, but everyone's curious about it. They want to know, but they don't want to ask, and there's nothing better than showing a picture of the toilet to show that we're all humans and that we're all accessible here. I'm going to give a good presentation. I'm a person just like everybody else. I note that Richard Alley in his masterclass presentation did a great job of this. He has an amazing and perhaps formidable reputation in science, but he showed a picture of him riding his push bike to work. And that was gold. It showed that he was an individual like the rest of us and that he was going to give a presentation that we would be interested in. Okay, let's turn it over to paleoclimate. Paleo comes from the word paleos, meaning ancient, and climate, here is a very simple definition, average weather over many years. So we could say that Paleoclimate is simply a climate that was prevalent at a time in the geological past before the instrumental record. And paleoclimate studies utilize evidence of the past environments that existed. So things like rainfall and temperature that changed as climate changed and that have been recorded in a natural archive. And by that I mean the geological records, perhaps ice or sediment. So those indications of the conditions that existed have been preserved. These things are called proxies, and some of the common proxies we use in paleoclimate studies are isotopes, chemical isotopes from either water or fossils. We can use the plant and animal fossils themselves to give us an indication of what the conditions were like, or we can even use the sedimentary rocks. So if we find features like ripples, we know something about the movement of water that has occurred in the past. I've popped scrap from Ice Age in here just to lighten up the heavy content that I'm talking about. So these proxies I'm talking about provide a substitute measure of a climate that existed in the past. So they are the biological, chemical and geological responses to climates and processes that have occurred in the past. A good example here is plants. So on the left-hand side I've got a picture of some fern fossils, 250 million year old fern fossils that have come from a sedimentary layer in the Transantarctic mountains. And I can show this to anyone, even a child, and they can very quickly see that it looks like ferns, things that you can see in your own garden. So proxies like this are actually very compelling. You can't argue with it. There it is, right in front of you, the evidence of past conditions. So we can unravel all of that proxy information that we can get from these records, and we can reconstruct the conditions or the climate that existed in the past. Now to do that, I have to introduce you to two key concepts, deep time and uniformitarianism. And I have to do this with my students all the time, so I thought this will be a good example of how to communicate complex topics in an effective way. These are some of the things I do. I use some memorable quotes, so something easy to remember about a concept. Here's a great one from Neil Armstrong. Geologists have a saying, rocks remember. And, well, obviously they don't really remember, but there are things about the rocks that will tell us about the conditions that existed in the past. What happened to those rocks? I often tell a few stories, and I tell stories about light bulb moments where the penny has dropped for me and I've suddenly understood a particular concept. So this is not so much giving analogies, but telling personal stories of my own experiences in learning. Let's talk about deep time. So we have big capital letters here because it's a very important topic. Deep time. Geologists have to grasp this concept. It's very difficult for us to think beyond our own lifetimes or perhaps a few generations. So let's consider that in a little bit more detail. We can all think about 1 year. It goes too quickly. We can all think about 100 years. What about 1,000 years? That's perhaps something we learned about at high school, some battles in the past, the Dark Ages, something along those lines. But when we get to 10,000 years, most people tend to glaze over a wee bit. Something to do with woolly mammoths and saber-toothed tigers, perhaps. Something to do with an ice age, maybe, or perhaps was it dinosaurs? No, most people can't remember. How about 100,000 years? That's still not very long, geologically speaking. How about 1 million years? So 1 million years is the basic unit of currency that geologists have to deal with. 10 million years is what we have to comprehend if we want to talk about the history of the ice sheets in Antarctica. If we want to go back to the history before the ice sheets, we need to comprehend hundreds of millions of years. So what about 1,000 million years? That's 1 billion. The Earth, as best we can tell, is 4.6 billion. That's 4,600 million years old, which is just a mind-boggling amount of time. So this is one method that I use to try and get people thinking on scales beyond a decade or two and actually into geological deep time. The other concept of uniformitarianism I want to introduce this chap here, Sir Charles Lyell. I call him Uncle Charles to my second year students. This guy was important in developing the idea of uniformitarianism. This is the idea that the processes going on outside in the real world today have always been going on. In other words, we can say the present is the key to the past. So rain has always fallen from the sky, water has always run downhill. It moves sand grains, waves wash up on the beach, and it sorts the sediment. It's illogical to think that water used to flow uphill. So the things we can observe outside today have always been going on. We can use that to understand the geological past and then use that as an analogue for what might happen in the future. Here's a great quote from Winston Churchill which summarises this idea. The farther backward you can look, the farther forwards you are likely to see. Of course, Winston Churchill wasn't talking about deep time and uniformitarianism, he was talking about global conflict. But nevertheless, it's a great quote that students remember to try and understand this idea that the present is the key to the past. All right, I want to share a couple of personal stories, some light bulb moments for me where it all made sense. So I visited the Grand Canyon a few years ago, and although I had studied geology and I knew about deep time, it wasn't until I stood here and looked into the Grand Canyon that the penny really dropped. I could look down at the bottom and see old metamorphic rocks, 2 billion years old, and then I could see all of the different layers of sedimentary rock. And these layers were deposited in deep oceans, shallow oceans, vast deserts that migrated across the area. All of the evidence is preserved right there in the rock record before me. And I can look away, but when I look back, it's still there. So it's very compelling. The evidence is there. And suddenly I got it. Deep time. There's 500 million years of Earth history and processes operating just like they do today, but with deep time. Here's another light bulb moment. This one was in Antarctica. While I was mapping some glacial deposits, I stumbled across this pavement, and you can see that there are ripple shapes on the surface. Well, it turns out the surface is 260 million years old and represents the flora of a shallow lake that existed way back in the distant past. And it struck me because I looked at the surface. It's 2 o'clock in the morning in a place where it hasn't rained for millions of years. There is no water. And yet I know what these things are because I regularly take my students to the beach in Wellington and I make them measure ripples. Ripples that are formed in just the last few hours by waves washing up on the beach. So we can measure the ripples and it tells us something about the wave height and even the water depth. Some very detailed information about the process that operates in real time. So standing in Antarctica looking at this old surface, I was suddenly aware that what I was looking at was a paleoclimate record of maybe an hour's process that happened on a sunny Wednesday afternoon 260 million years ago. So it was a eureka moment for me where suddenly things made sense. So I like to tell these stories to try and get my point across to the students. All right, let's move on to Antarctica and paleoclimate records. We can look at ice cores, which give us a very detailed record of the last million years or so. But if we want to go back further than that, we have to look at the geological record. And there are two ways to do that. One is by looking at the outcrops, which are exposed in the mountains, which is great, but it's rather fragmentary. Or we can drill into the sedimentary layers around Antarctica, which is what I'll talk about later on in the presentation. Here's a good example of how paleoclimate data can be used to reconstruct an environment. This is an artist's impression of the Antarctic Peninsula 85 million years ago. And you can see there are lots of different types of trees here, lots of different types of fern, and there's even a cheeky little dinosaur poking out from behind the tree there. So yes, this is an artist's impression, but it's a scientifically informed one. This is based on years of investigations of Alexander Island. So I'll summarise that a wee bit and say that the sedimentary rocks contain fossil leaves, pollen, wood and flowers that were growing in Antarctica in a fairly warm climate 85 million years ago. If you do some statistical analysis of all of those that fossil material, you can paint a picture of a forest canopy with conifers, ginkgos and podocarp trees, and an understory with ferns, liverworts, mosses and shrubs. And the way this works is by taking the paleo information, the fossil information, and comparing it with modern similar plants. So we can look at the ferns and the trees and get an idea of the kinds of temperatures that those kinds of trees like. We can get an idea of the rainfall. So it gives us very specific data about things that existed in the past. So we know that 85 million years ago, the climate was about 20 degrees Celsius with a rainfall of about 2.5 meters a year. So a warm, humid, subtropical environment. The unfortunate thing about the outcrop record is that sometimes it's not there. So here's a cartoon that I use for my students showing the Transantarctic mountains. The rocks that are exposed in the mountains are very old. So if we're interested in the last 50 million years or so, which is when we think the ice sheets formed, we're out of luck looking at the outcrop record. The rocks we need are either beneath the Antarctic ice sheet or they're under the ocean off the coast of Antarctica. And this means if we really want to look at those rocks, we have to drill for them. And that leads us on to drilling back to the future, the Cape Roberts project and the Andrill projects. So both of these projects were drilled into the seafloor off the coast of Antarctica, off the coast of the East Antarctic ice sheet on the Ross ice shelf. So seismic lines had identified a very thick package of sedimentary rocks here. So conventional drilling equipment was used, but with some modifications to set it up on sea ice and ice shelf platforms, and we drilled into the seafloor. So I'd like to stop and talk about communication tip here. Clearly the drilling projects have involved hundreds of people over many years, and the science is complex and recorded in many different papers and volumes. We can't obviously summarize all of that in one place without some good diagrams. So simple, vivid, scientifically informed diagrams are very valuable. And I'm going to use an example from the Andrill Flexibit posters. And you may have seen this one already in the first masterclass. It's a fantastic diagram, very well drawn, but importantly, it's been drawn with the help of the scientists. So it is scientifically accurate or scientifically informed, even though it's a cartoon. These posters were produced in multiple formats, PDFs, JPEGs, TIFFs. They were produced in multiple languages, and they are great for many different purposes, from giving a PowerPoint presentation through to giving a conference poster. So I have taken bits of these posters and spliced them into various talks, and I'm going to show a few of those to you now. So I've simply cut out the picture of the drill rig here. And this summarizes how the Antarctic drilling works. We've got a riser connecting the drill rig through the ice shelf or the sea ice down to the sea floor, and then we drill into all of these sedimentary layers. There's some amazing technological challenges had to be overcome to actually get this tube of rock out of the ground and up to the surface so the scientists could see it. And I think Betty is going to talk about some of that in just a moment. So I'm going to talk a little bit about the types of analysis that were carried out on the drill core once it was brought up from the seafloor and into the science lab. The first thing we did, of course, was describe the sedimentology. What were the sediments like? A layer by layer description of all of the sediments, looking at its grain size, looking at its fossil content, looking at other features that might tell us some clues about how it was deposited. We can look at the rock properties, the density, porosity, and magnetic susceptibility. We can look at the rock fractures, which tell us something about the faulting and the deformation. We can scan the core, which give us images of the sediments and any of the faults in there. We can scan it using X-ray fluorescence, which tells us something about the composition of the core. We can actually use a hand lens and look at the sand grains and the pebbles themselves and try and work out where those grains have come from. That gives us some idea of what was being eroded and where it was being transported before it was deposited. We can look at the paleontology, so that's examining the fossils, the large fossils, the small fossils, everything from mollusks you could pick up in your hand through to very small fossils that you can barely see with the naked eye. Foraminifera, diatoms, which are little plant fossils, pollen and leaves. Anything that can give us some insight into the environmental conditions that existed at the time. And of course we look at the rock magnetism, and this is something that Betty was involved with during the Andrew and Cape Roberts projects, looking at the magnetic signal that has been locked up in the rocks, and that provides us with some control over the age of the sediments. So let's talk about some of the results from the drilling. And this diagram here, I've got a lot of information here, but let's start off with, it has time on the left-hand axis, and it has change in global temperature from present along the bottom. And this diagram has been put together from evidence from a whole lot of drill cores. The DS, DP, and ODP are drilling from ships in the deep ocean. A great record, but rather fragmentary. And then we have the CRP, the Cape Roberts project, and the Andrew records close to the margin of Antarctica. If we put all of this together, it's telling a story of falling global climate over the last 60 million years. We now know, because of this drilling, that the first Antarctic ice sheets began about 34 million years ago. So we went from a warm greenhouse world through into a slightly cooler world where we had ice caps in Antarctica that oscillated. And this continued on for about 14 million years through what we call the transition world. At about 14 million years ago, global climate cooled again and the persistent Antarctic ice sheets developed. So there has been ice in Antarctica continuously for the last 14 million years or so. What's not shown on this graph is that even though the ice was there permanently, it did wax and wane. It was growing and shrinking through global climate cycles for the last 14 million years or so. So let's look in detail at the record from one of the Andrew cores. Scientists were able to recognize, out of all of the layers that were drilled, 3 typical and repeating types of rocks. So I've broken them down into 3 basic flavors. And the first one is called diamectite. And this is basically a mix of pebbles and sand and sometimes boulders. It has pebbles with particular shapes and even with telltale marks like striations from sliding ice. It tells us of a particular depositional environment which we can interpret as being deposited beneath a glacier, beneath a grounded ice sheet. So these act like giant bulldozers pushing a big pile of very poorly sorted sediment along underneath the glacier. So there are deformation features in this which have been produced by this glacier moving along. So this reconstruction of the environment shows that ice was grounded or on the bottom, sliding across the surface at the drill site, and that we were in full glacial cold conditions. So Antarctica was covered in a much thicker ice sheet, the glaciers extended off the coast, and sea level around the world was about 15 meters lower than it is today because the water was locked up as ice. The next kind of rock unit we described in the drill core was stratified diamectite and sandstone. So this had components of the poorly sorted pebbles and sand, but it also had layers of nicely laminated and stratified sands. So the interpretation of this is that it's very similar to today's conditions, where we have a floating ice shelf fringing the grounded ice sheets. The sediments reflect the fact that there are parts of the sediment deposited by the glacier, but also sediment being deposited by meltwater flowing out beneath the glacier, and sediment being deposited from icebergs that are carving off the ice shelf and dropping stones down to the bottom of the sea. So our paleoclimate interpretation here is of an Antarctica with large ice sheets but smaller than full glacial conditions, and ice sheets that have large floating ice shelves extending around the margin. The third type of sediment that we recognized in the drill cores was called diatomite. And so this is a sediment that's made up almost exclusively of the remains of plant plankton, things called diatoms, which live in the upper layers of the ocean. They're very small plants, they photosynthesize, and when they die, the remains sink down to the seafloor. So the interpretation of these is that we've got much warmer conditions and we've got open ocean. There is no ice present here, so we don't have the diamectites bulldozed in by the glaciers. We don't have any indication of ice at all, not even any floating ice. So open, relatively warm water conditions, lots of photosynthesis going on, and a rain out of all of the plant material down to the seafloor. So our interpretation of Antarctica now is that the ice sheets have retreated, the ice shelves have disappeared, and possibly even we've lost a large part of the west Antarctic ice sheet. So this is full interglacial or warm conditions where we have a sea level that's perhaps 10 meters or so higher than present. So we can put all of that stuff together, and the scientists on the Andrill program recognized that these three distinctive types of rocks always occurred in a very repeated pattern of layers. And so they are telling the story of repeated ice advance and retreat, the growing and shrinking of the ice sheets over Antarctica. That, of course, is telling us about the repeated cyclicity of climate. So warm climates, the ice sheets and shelves shrink. Cold climates, the ice sheets and shelves grow. So we've got our 10 meters of sea level rise in the warm climates and our 15 meters of sea level fall during the cold climates. And we've got our cartoons here from the Andrill Flexibit showing our interpretation, our cartoon interpretation of those environments through time. If we look at the Andrill record overall, we see that there are actually dozens of these cycles of these three different rock types over the last 5 million years. So we have a very dynamic growing and shrinking, advancing and retreating, warm and cold ice sheets and climate in Antarctica. It turns out that the periodicity of these cycles was on about a 40,000 year time period. It turns out that that is known as Milankovitch cycles, and I haven't got time to go into Milankovitch cycles, but they changes in the amount of energy that the Earth receives from the Sun based on the tilt and wobble and change of the Earth and the change in orbit around the Sun. So it turns out that this is the pacemaker for changes between glacial and interglacial records. The important thing I want to point out here is that parts of the Andrill record and the diatomite layers showed that there was open water existing at the drill site at times in the past, meaning that the Ross Ice Shelf and the West Antarctic ice sheet completely disappeared when we know the conditions were only 2 to 3 degrees warmer than now, and that CO2 was only at about 400 parts per million, very similar to today. So that's giving us an idea of perhaps what to expect in the future. That leads me on to my final few slides about using the Paleoclimate record to inform the modelling. So sophisticated computer models can now examine the interaction of the different climate system components, the ice sheets, the ocean, the atmosphere, and see how they change through time. The Paleoclimate data provides the ground truthing for those models. So we can run a model, turn up the carbon dioxide or turn up the temperature and see if it recreates the conditions that we know existed in the past. So these models have been done many, many times, and I've got a little example here from DeConto and Pollard showing one of the reconstructions. And I don't think it's going to run for me at the moment. Never mind. What the models show is that the ice sheets are very sensitive to changes in carbon dioxide, they're very sensitive to changes in ocean temperature, and that they are paced by changes in the Milankovitch cycles. So the models are now good enough to be able to recreate the exact conditions that we encountered when we drilled the Andrill drill cores. So we know the models are working pretty well. That means we can now use the models to start predicting the future. So lessons learnt from the Pliocene 3 to 5 million years ago are now informing what might happen in the future. So here's a model from Pollard and DeConto and Pollard, a recent one. On the left, we've got a picture of Antarctica. using a pre-industrial carbon dioxide level of about 280 parts per million. Now, this looks very similar to Antarctica today, even though we have 400 parts per million, because the system has not yet responded to that increase in carbon dioxide. But if we play this model forward using 400 parts per million CO2, we will expect a 5-degree increase in ocean warming. And this is what the model tells us is going to happen. We will lose the ice shelves around the margins of Antarctica, in particular the Ross Ice Shelf, and we will lose most of the West Antarctic ice sheet, meaning that sea level rise from Antarctica, if we keep going the way we are, will be in the order of 7 meters. We can add in another 7 meters from Greenland, and we get up into the order of 14, 15 meters of sea level rise. There are still questions about the rate and timing of when this will happen, and there is a lot of research going on at the moment. So I'm going to just show quickly this slide. It's hot off the press. This is results of new modelling from Pollard, DeConto and Richard Alley, just out in the last few weeks. And it suggests that the rate of sea level rise might be a lot faster than we have been thinking. And this is because they can now add in the wild card, which is marine ice sheet instability. And this is what Richard Alley talked about in his masterclass a few months ago. The idea that warm oceans can undermine the ice shelves and trigger a runaway collapse of the ice shelf. If that was to happen, then we might expect perhaps more like 2 meters of sea level rise by the year 2100, far above the 1 meter that is currently predicted by the IPCC. So lots more work to be done here. So the take-home points here are not so much the details of the paleoclimate record or the models, but rather that paleoclimate studies and climate modelling have improved our understanding of how the climate system works on a range of timescales. In particular, we now understand better the links between the greenhouse gases, the Milankovitch cycles, global temperature, ice sheets and sea level, and it's highlighted how important Antarctica and, I should add, Greenland are for the climate system. So the insight gained by looking back at the past is now providing the knowledge to begin looking forward. So perhaps I could remind you that the present is the key to the past. It now seems that the past really is the key to understanding the future. So I'm going to finish on this slide here, and if I was asked to sum up my teaching philosophy in one sentence, this would be it. Tell me and I will forget. Show me and I may remember. If you involve me, I will understand. So I think that is perhaps an appropriate place to hand over to Betty. Thank you.
Thank you, Cliff. That was wonderful. We have a couple of questions for you. We'll see if we can get through a couple of these, and then if it's taking too long, we'll put them on the discussion group. One of the questions is, you talked about 1 meter of sea level rise might happen by 2100, and then you said maybe 2 meters. And I think you've probably touched on the answer to this, but is that expected to rise by meters, centimeters, or can we expect some sudden rises? And I think you've kind of touched on that a little bit.
Yeah, look, that is a really good question, and I'm not particularly well armed to answer it, but the research that has come out in just the last few weeks is suggesting that the dynamical response of the ice sheets, this sudden runaway collapse, is something that we really don't understand that well, and the potential for very rapid rises in sea level, so you know, over the matter of decades, to get to that 2 meter sea level rise is now a very real possibility. And of course that's not something that's been included in the last IPCC because that research hadn't been through peer review process yet. So there is a lot of effort now to try and understand that wild card, the potential for the marine ice sheet instability. So I guess I'd just say watch this space.
Okay. Thanks. Another question was, when you talk about Lyle and how things have happened in the past and are happening today, how do you avoid the climate deniers that say we're experiencing a regular climate cycle?
Yeah, this is an old one that comes up again and again. So, look, it's been paleoclimate scientists that have discovered that the world has been through many climate cycles before. It's absolutely true, and no one's trying to hide that fact. There have been warm climates, cold climates, glacials, interglacials, long before people were interfering with the climate system. But the thing is, we have now modified the atmosphere on a much faster rate than ever before. So we can't claim that it's just a natural cycle and that it doesn't matter, because we have now increased carbon dioxide to 400 parts per million on a much faster scale than it would happen naturally. We have yet to see the natural system respond to that, but we know that it will respond. So paleoclimate tells us how the system reacts. It's not a way to say it's not our fault and that it will happen anyway. We do understand how the system operates, and we know that we have modified one part of it. So the science tells us things are going to change, and they're going to change because of what we've done. Okay,
great. And here's a couple of questions that hit close to my heart because they're questions about the Andrill work. But is the core analysis done on site, or does this wait until the cores are returned to labs off the ice?
Yeah, a lot of the core analysis is done on site, and it's important to look at the core quite quickly when it comes out of the ground, and we get to see a lot more detail. So for the Cape Roberts and the Andrill projects, we had big labs set up at the drill site. So the core comes out of the ground, and within a matter of minutes, it's in the lab, it's being cleaned up, it's being examined, it's being sampled, and then it is transferred back to better laboratories back at McMurdo and Scott Base, and a lot more detailed analysis is done there. So a fairly complete description and initial analysis is done on the ice, and then over the subsequent months and years, more sampling and more detailed analysis is done in a variety of labs around the world.
Thanks. We just have two other questions. Are the pictures of the different types of rock magnified?
No, they are almost exactly to scale. The drill core, when it comes out of the ground, is about 5 or 6 centimeters wide, and so those are literally just direct photos. They might be a little bit squashed on my PowerPoint presentation, but they're pretty much to scale. That's what it actually looks like.
Okay, and then the last question was, how deep did the Andrill project drill, and how does that correlate to years in the past?
So the Andrill project, the MIS project, was the deepest drill hole in Antarctica. It got down to over 1,200 meters below the seafloor, so that's 1.2 kilometers. So that core reached back to about 15 million years. The tricky thing is, it depends where you drill on the seafloor for the age of the sediments. For example, the Cape Roberts project was much shorter core, it was only 600 meters, but because of the erosion on the seafloor and where the faults are, when we started drilling, the rocks were already 15 million years old there, so we drilled from 15 back to 34 million years. So the actual amount of rock you drill does not necessarily correlate to how far back in time you're going. It depends on the individual site and the location of the faults.
Okay, thanks, Cliff. And if there's more questions, be typing them into the question box, and at the end, if we have time, we'll post some more questions. Thanks so much, Cliff. If you'll go ahead and mute your microphone, and Betty can unmute hers, and I'm going to make Betty the presenter now.
Okay, Louise, can you see my screen?
Yep, we can see your screen. You're not in presentation mode right now.
No, I know. I just wanted to be sure you could see it first.
Yep, we can see it here, and everything's great.
Okay. I'm ready to go. Thanks, Cliff, for that great presentation, and welcome to everyone. Hang in there. Mine won't take as long as Cliff's. We need to be done in about 35 minutes. I want to thank you for being part of this master class. Unlike Cliff's nice weather in New Zealand, we're having a wintry mix of snow and sleet today, so a little bit more like Antarctic weather. As Louise mentioned at the beginning of the presentation, I am a fourth grade educator, but I've had quite a unique career with 3 Antarctic projects and sabbaticals, going to Antarctica 3 times and working alongside scientists. So that's really quite different. Getting involved, first of all, with TEA, as Cliff mentioned, with Cape Roberts, this was my first experience in a multinational project involving scientists from around the world. And this was really my first look at integrating science research and education. The program goals of TEA were to immerse the teachers in the research experience as part of our own continuing professional development and inform teaching practices through this research experience. And they wanted us to bring polar research into classrooms in innovative and engaging ways. And if you look back even in the 1990s, then when I was part of this program, there was a movement back then to establish and grow this idea of a polar learning community, similar to PEI's goals now in 2015. And my collaboration with Cliff and others on the different projects I've worked with is a great example of expanding that polar learning community and encouraging educational outreach. So just a quick look at Cape Roberts. This was my first participation in the research experience back in 1998. And as Cliff mentioned, he was just an early career scientist getting his PhD. And what I learned was that the scientists could see that my involvement was helping convey their research to a wider audience. So what was a way of teaching scientists how their research could be conveyed to children and teachers and adults around the world.
Betty, I'm going to interrupt you for just a second because your slides are not in presentation mode, so they're not advancing.
Oh, they are on my screen. They are on my screen. I'm in presentation mode.
All we're seeing is your slides down the left side and your first slide, or at least I am. I hope I'm not the only one, but I think that's what everybody's seeing.
Okay. I don't know what. Shall I close it and try to launch it again?
Why don't you click off of, go to the view of your navigator or whatever, I've forgotten what it's called in PowerPoint, and then click back on the presentation, the slide.
What do you see?
Betty, I'm looking at the bottom, down at the bottom on the very right-hand side, you have 3 different buttons that you can click on. Are you clicked on the screen on the right side?
I have something on the top of my screen, Louise. I'm seeing it in presentation mode. So I don't know if I end the show and relaunch.
I worry about that because it might take a long time, but if you could just click out of the mode that you're in into another mode and then back into presentation mode, maybe that'll kick it in.
Well, I've done that several times. Are you still seeing the slides down the side?
Yeah.
I don't understand why it's doing that. It didn't do this the other day.
If any of my tech people online have any ideas here, help me out.
Okay, I started back from the very beginning. Are you seeing it in presentation mode?
No.
Louise, you might have to launch your version.
Are you seeing it, Gary?
No.
I don't understand.
Louise, if you have a copy of the presentation, you might have to just take the screen and she'd just have to tell you to advance.
Yeah, Betty, you want me to try that?
Did that work, Louise? I completely got out of it and relaunched it.
No.
No.
Okay. I apologize to all of you online. Let me pull up.
You can try taking her out of screen sharing mode and then put her back into screen sharing mode.
Okay, thanks. I'll try that.
I also closed out the PowerPoint and reopened it.
Okay, sorry for the little glitch here. I'm going to take back the screen and we'll try that again. All right. Betty, I'm sending it back to you again. Let's try it one more time. Otherwise, I have your presentation and can show it, but let's try yours one more time.
Here we go. We got
now
it.
we've got it.
Now we've got
Yep.
it? Okay. So I'm just going to back up one slide to just start over with the Cape Roberts project. And then this slide shows immersion in the science, capturing that process of science as a field experience. My scientist that I was assigned to, Dr. Ken Virosub from the University of California at Davis, was part of the Paleomagnetology team. And our team represented a U.S. scientist, a couple of Italian scientists, and 2 scientists from New Zealand, one of whom was working at Otago University at the time, and the other one working in the UK. So this was my first chance to really dive into the science and get this very hands-on experience. And going back to what Cliff said earlier in his talk, it's important about involving me and I will understand. So doing the science work, I was able to then convey that work to the public through my communication. So part of our responsibility was to post journals and upload digital images. And if you look at the screen here, you see these old computers, that like just mammoth old computers. And the digital images we were uploading were from a Sony Mavica, where you put a floppy disk inside of the camera. So it's really ancient technology now. It's much easier to do this. I was answering letters from students and teachers, and that was back when my school district barely had email access. They actually had to get email access for my experience down in Antarctica. And we did a lot of telephone interviews because that was the easiest way to communicate from the field. What I found that I really loved was not only the experience, but after the experience was over and transferring this to classrooms. So the upper left slide shows Dr. Virosub in my classroom talking to my students about the science and ways that I showed that science to my class through a flow chart about the Cape Roberts project, or presenting to different classrooms in my school district or around the country or around the world. I also liked in developing activities and educational materials. And one of the things I tried to do was take that idea of the core, because we couldn't bring any core back with us, but try to take that idea and show students what that might look like. So I developed this recipe for a core science activity using both edible and non-edible objects to kind of simulate a core, and then look at the different rock layers and the different fossils that you might find in the core. I also wrote some grants to get icebox, we called them the icebox, teaching trunks for teachers that included videos, posters, puppets, photographs, all kinds of teaching tools that could be loaned to teachers in Illinois. And that was provided through Delta Kappa Gamma Society International. And I wrote a second grant when I made this connection with Gordon Bain, who used to work at the Australian Antarctic Division, and we made this contact through another program, and we decided to start what we called a Sister States program to link educators in Tasmania, Australia, with educators in the U.S. And so I wrote another grant and got a teaching trunk and brought that to Australia, and Gordon and I went around Tasmania talking to teachers, kind of linking to their Antarctic program. So there's another international component and linking with a scientist or collaboration. Gordon introduced me to a woman named Coral Tulloch. And Coral's an author and provided this very valuable literacy connection, because as an elementary teacher, we have to show things across the curriculum. And so using her fiction and nonfiction books dealing with the science and learning about Antarctica, I was able to provide a literacy connection for my elementary classroom. So all of this outreach and classroom transfer kept me really busy from 1998 until 2006 when I was part of the Andrill Education and Outreach team, going down for the MIS project and working again with Cliff and others that I had met in the Cape Roberts project. So again, another multinational project, but very different. The drilling logistics were based at Scott Base and the curatorial team that was based at the drill site, but most of the scientists were based at McMurdo Station. And you can see by the map that Scott Base is very close to McMurdo, just a couple of kilometers away. Scott Base was very close to where we were drilling, so we could easily go back and forth from McMurdo or Scott Base out to the drill site. The other big difference was that instead of being a teacher working in isolation with a science team, there were 6 teachers, part of what we called the ARISE team of teachers, Andrill Research Immersion for Science Educators. And the U.S. contingent was myself, Luann Dahlman, who worked as a curriculum writer, very talented curriculum writer, out of Phoenix, and Vanessa, who taught in New York City. So she taught in Spanish Harlem, total inner city experience, and I visited her classroom before we went to Antarctica, and here I am in a suburban Chicago environment, so very different. Matteo Catadori teaches high school in New Zealand. Italy. Julian was a high school teacher in New Zealand, and Alexander is still a professor at Heidelberg University in Germany. So there was a real mix of what we taught, what age groups we taught, how we taught, and that was very valuable as an educator to have these people to bounce ideas off of and to work with before we went to the ice just a bit, but while we were there and then after our on-ice experience. The ARISE program had similar goals to TEA, so we all had proposed projects and activities that were going to reach out to a broader educational community. We were all immersed in the Andrill science on the ice. We had daily science activities. We were part of the team. We all posted blogs on the Andrill website, and we had ongoing communication with students, teachers, and people around the world. And then we all continued outreach efforts in various ways and curriculum projects after our ICE experience. One of my personal goals is to change people's perspectives of what a scientist looks like and what scientists really do. And I've done this experiment in my class, this activity, every year for probably over 20 years, where on the first day of class, I'll tell my students to draw a picture of a scientist at work. And that's the only real criteria I give them. The picture on the left is from one of my college students, one of my pre-service science method students. And the other one on the right is from one of my 4th grade students. And you can see that even though there's an age difference in the students, there's not much difference in the picture. They all portray a scientist as this person with wild hair and glasses, working in a laboratory, mixing chemicals and blowing things up. After I've taught my students about Antarctica, you can see that, yes, the pictures are very primitive, they're not well developed artistically, but the theme of the pictures is much more realistic in terms of what I've been teaching them about science in Antarctica. So I think there is a real value to bringing that science into the classroom and to then having kids learn what's going on right now in terms of science research. So again, the pre-ice and post-ice presentations are really important, especially before we went down to the ice, because we wanted people to follow what we were doing, to follow our blogs and get involved in the research as it was unfolding. And I teamed up with Matteo and Julian in New Zealand, and we did some presentations to try to get some interest in New Zealand to follow us as well. And as Louise mentioned, she and I have done many, many workshops together since we were involved with Andrill, and even before that at the Museum of Science and Industry in Chicago, and also at the Field Museum of Natural History in Chicago, and in other locations as well. So what would a day look like in McMurdo? Well, we'd start off with a daily meeting about what's going on in terms of the science of drilling, and we would take what's called a core tour. And we would be led through the core lab and looking at the boxes of core that would be sampled that day. And the scientists would then later on flag the core, put a little flag where they wanted to take a sample that day. And then I would spend a better part of the day working on the scientific work for Andril, whether I was working with the Forum, the Paleontology team, or being part of the curatorial team or Paleo Mag team. It was a very hands-on experience, and that is involving me so that I would understand the science and being able to then translate that through observations and interviews and delivering that in terms of blogs, email contact, video conferences, and working with our media specialist, Megan Berg, on producing video journals. We also met as ARISE educators every day together, often with the scientists, to ask questions about what was going on, to clarify the science, and giving us new information on geology and Andril that would help us better understand what was happening in real time. In terms of graphics, I know Cliff touched on this just a bit. He also mentioned know your audience, and I think that's really important. Knowing your audience through this particular graphic has helped explain to people what I did as an educator, because a lot of people just thought I was on this trip to Antarctica and they weren't sure exactly, who I was impacting. If you look at the big red arrow between the Andril scientists and the ARISE educators, we taught each other. They taught us about the science, but we taught them how to convey that science to different audiences, to students, to other teachers, to school administrators, to the media, to families, and also to work with our local and national institutions, museums involved in scientific outreach. So I've used this graphic for many different audiences, and this was kind of one of those light bulb moments for me as well. Looking at the parallel development of the projects, because all the ARISE educators were working on their own projects, but we were kind of working in tandem. And there were lots of mutual benefits, that support of our peers and communication on our projects and our activities, the multilingual, multicultural perspective, which is very unique, and also helping each other organize professional development events and transfer of the experience. One of the things I really got turned on by was the STEM aspect of this whole Andril project. I didn't get to see much of Cape Roberts in terms of the drill rig because it was very remote, and we had one helicopter trip to see the workings of the drill site. But with Andril, because it was closer, I had the opportunity to go out to the drill site multiple times and see how this whole thing worked. What I found was that people really wanted to know how the scientists got this core. They had no idea how the core got in those boxes and got delivered to McMurdo. So I took a step back and looked at my audience, whether it was the children or the adults, and started to explain this process of the drilling, which is really a huge STEM piece, a STEM aspect of this project, the functioning of the drill, the various drill bits and core diameters and the process of drilling. So if you look at this particular slide, Cliff showed you that diagram with the drill string that was embedded into the seafloor. Picture number 1 shows where the tools would go down inside that sea riser. And then picture number 2 is the core barrel that was retrieved. In picture number 3, the drillers are sliding that core barrel on a kind of a trough. And in picture number 4, you can see the sediment that's been retrieved, that's been pushed up into the core barrel, and then that is taken into the drill site lab. Picture number 5 shows the different sizes of drill bits that were used. They started out with a larger drilling bit, and then as the hole became slightly unstable because of going down farther into the seafloor, they would switch to a smaller and smaller drill bit. So by the time they ended up with the smallest drill bit on the right, instead of having a 3-meter length of core that was retrieved, they had a 9-meter length of core that was being retrieved. And in this slide here, you see in picture number 1, the drillers and the curators are helping to carry that across from the drill rig over to the on-site drill laboratory window, which is in picture 2. They're sliding that right into the laboratory at the drill site, where Alyssa, one of the core techs, was cleaning up the drill, and as Cliff was talking about, prepping the core for the different science discipline teams involved with Andril. So at that point, the core is still whole, is still a tube-shaped. When it's brought into McMurdo, they actually cut the core into 2 equal halves. Okay, they sliced it right down the middle, and one half became the working core that was actually sampled and bits and pieces were taken out of it, and then the other half became an archive bit that was put into a core storage facility. And so the picture in the bottom right shows how the core is being scanned to get high-resolution digital images that can be used immediately in the core laboratory. The boxes of core were sealed and wrapped, and we might not see the boxes of core that I was working on in that lab for maybe a week or so, because there was a little bit of lag time between when the core started coming in and the core from the drill site and the core that was being observed in the laboratory. So, as Cliff already mentioned, the scientists examined a wide variety of core and identified those 3 major scenarios. The other thing I really enjoyed, and Louise, you was very responsible for this particular educational outreach component, we did teleconferences, linking classrooms to science on the ice. So Louise was down in McMurdo the season after I was there for Andrel, and she was the education outreach coordinator the year after I was on the ice. And so we had my students linked with a scientist, and just by telephone and watching a PowerPoint in my classroom, and as I would advance the PowerPoint slides, the kids could ask questions. Well, the kids loved it so much that I got some of my friends from the year before when I was down there, Alyssa, who was a core tech, JR, who was an engineer and mechanic, and Christina, one of the scientists. And again, I could teach these children in my class the process from getting the core out of the seafloor all the way to when the scientists were examining the core. So again, showing the whole picture, not just the scientists looking at the core. And I think that's really important. One of the things, I know we don't have much time, but I want to touch on the Flexibit. We've talked about this in the first master class with Nell and Richard Alley. Nell was explaining some of the Flexibit activities. The Flexibit got its name from being a flexible exhibit. So it's based on 5 major themes where kids can become the teachers, and it's all there to increase public understanding of Andrel and climate science. So you can get this on the Andrel website, and we can talk more about this in the discussion in the next couple of weeks. Basically, I've done this activity in my classroom for the past 7 years. We've hosted a Flexibit. So my children are learning how to teach others. I have 9 and 10-year-old students in my class who become experts in one little component of the Flexibit, and they teach their peers, and they also teach their parents. It's a great model that builds knowledge and confidence and experience for these students, and they speak with great pride and confidence as they wow the parents with their knowledge on climate science. So you've seen this poster already with Cliff, and we've talked about the importance of good scientifically informed graphics, and that's where the Flexibit provides a wealth of these scientifically informed graphics that can be used in many different ways by scientists, by teachers, by informal educators, and I think that's important to remember that it can reach a variety of audiences. So one of the activities I want to touch on briefly is mixing up a model rock core. And you'll be able to access this through the discussion, but I want to explain a little bit about this. So you're going to be taking plastic protective tubes for fluorescent lights, about 2 feet long, and you'll need 2 PVC slip caps to seal the ends of the tube, as you can see in this photo on the slide. You're going to use stones, gravel, sand, fine silt, crushed ice to show the sedimentary rock types identified as part of the Andrel science research. So it could be sedimentary processes under an ice sheet, it could be sediments under an ice shelf, or sediments in an open ocean scenario using green sand to represent the millions of diatom skeletons that would pile up on the sea floor. And all of this is explained in much more detail. We're short on time, so I'm just going to kind of cut to the chase and show you what my model rock cores might look like. And I can't remember where I saw this stand. I certainly didn't think of this design myself, but I had a carpenter, a parent in my class who was a carpenter, and I showed him this picture, and he was able to build me the stand, which was great. Instead of having the model rock cores laying horizontally, I was able to stand them up vertically, which I think was actually easier for the children to understand the deposits of the different kinds of rocks and sand and silt and gravel. And the green on the right, you can see the green sand being deposited into the sediment tube, and that would show those diatom skeletons. The other activity in theme 3 is building a drill site model. And again, getting to that STEM component. The kids wanted to know how the core was obtained. And so we built a model of the Andrill drill rig and simulated the drilling process. So you take a kind of a gift box on the top that represents the ice shelf or the ice of the sea ice layer. There were 4 yardsticks in a box on the bottom holding up the top box, and that was draped with blue cellophane to represent the ocean. And then there's brown butcher paper on the bottom for the layers of sediments on or below the sea floor. And you can see the lines that I drew on the butcher paper to represent the layers of rock. And then you have a smaller diameter PVC pipe that represents the drill, the sea riser, where the drilling equipment and the pipes would go down inside of. And finally, you've got a string with a small magnet on the end of it. And then there's 3 wooden dowel rods with 3 sample cores, 1 for each scenario that Andrill identified. And you can put the string down with the magnet, and each little drill core has a thumbtack in the end. So the magnet will attach and you can bring up those model drill cores and show people how they obtain the cores from the drill rig. Very simple, very effective. And then you can see on the right my students explaining this drilling opportunity to their peers. And I was lucky enough to get from Alex Pine, our chief of drilling operations, the year I was there, he gave me one of the drill bits that wasn't going to be used anymore, and I'm able to use that as another prop or teaching tool in my classroom. The more props you have, the better the kids understand what's going on. And Cliff actually made me that tube. You can see the gray, kind of a foam example of a core, and he labeled it the working and archive half of the core. So it's really a good model for my students. So I think in closing, we have this opportunity as educators and scientists to teach about these unique places, the polar regions, and to keep students excited about learning through presenting these really interesting, unique places, and to share this process of science and the research, and also to keep our own learning alive and enhance our own professional development. And I think my collaboration with Cliff has helped us both become better educators in the 17 years that we've been collaborating. And I think it's been a huge part for both of us in terms of our careers as teachers. So thanks very much for listening, and I don't even know if we have time for any questions, but if we do.
Hey, Betty, thank you. That was great. We had just 2 quick questions for you. One, could you define STEM for any teachers that might be in countries where that acronym isn't used?
Yes, and I should have done that. STEM stands for science, technology, engineering, and mathematics.
Okay, and then along with that, in the U.S. with the Next Generation Science Standards, there's a big influence on engineering. Are you working on any engineering lessons about the drilling with your students?
Yes, we actually in our district, we just started having a STEM kind of encore class, kind of like gym, music. STEM is one of our encores. And Louise, I'm getting a whole bunch of feedback. Okay, that's better. Thank you. And yes, we are working on engineering. The kids love knowing about the models. They like to build the models. They like to know how things work. And that was a big aha moment for me, because I had to take a step back and really start explaining that when I was writing in my blogs and writing to students. You know, I was talking about the core, the core, the core, and I found that I had to take a step back and talk about that technology and that engineering process that allowed the scientists to get the core to work on and do their research. So that was really important in my own learning.
Okay, thanks again so much. And I'm going to take the screen back real quickly here. Give me 1 second. Okay. Okay, as we bring this webinar to a close, just a couple of reminders. We want to be sure that you sign up for the discussion group, which will start tomorrow at polareducator.org/members. And again, any technical problems, go to polareducators2@gmail.com. Whoops. Oh, I'm sorry. I am in the wrong spot here. Hang on. Just wanted to point out again another address. You can go to andril.org/education for the 2 activities that Betty mentioned, and during the discussion she's going to talk about another one that relates to these 2. And a couple of reminders, join that online discussion. The discussion forum will take place starting tomorrow until the 20th of March. And to earn the PEI certificate of participation, there's a syllabus on the PEI website. And basically, you'll be taking a pre-survey if you haven't already done that, and taking part in the discussion, and then doing a post-survey. So we hope you'll join us for that. In fall 2015, we'll be having another masterclass, and it'll be based in the time zone of Portugal. And I just want to thank Cliff and Betty so much for being with us tonight and allowing us to record this for an archive version too. We know that this takes a great deal of time to prepare for something like this, and so thank you so much. And I also want to thank those of you that are participating tonight. We appreciate your time, and I would just want to point out that anytime a project of this size is undertaken, it takes a lot of people to make it happen. So I want to thank the masterclass and website working groups, and also the executive committee of PEI. Thank you so much. And if you have any questions, feel free to email polareducator.org, and we hope to see you on the discussion group. Betty and Cliff, thank you again. Good night, everyone.
Yeah, not all.
Louise,
Yeah.
you need to stop the recording.
Oh, thank you.